I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on electrostatics, charge transfer, the electric forces between those objects, and the behavior of charge in materials. All right, in this video, we're going to talk about electrostatics, which is electric charges, the forces between them, and how the charges behave within materials. So let's first review the structure of an atom. So we know that it has a positively charged nucleus surrounded by electrons in that electron cloud. And we know that the positive charges are going to attract those negative electrons, and the electrons are going to repel each other, so they're going to push outward away. The electrons are the movable charge that produces the net charge. So we may have two electrons that are lost on an atom, which gives it a +2 charge, or two that are gained, and that gives you a -2 charge. So charge we know comes in positive and negative, and that was named by Benjamin Franklin when he did his famous kite experiment. It has a specific quantity. The elementary charge, E, is the charge of one electron or one proton. And the charge is 1.6 times 10 to the negative 19th coulombs. And this was discovered by Robert Millikan in his oil drop experiment, which suspended charged oil drops in between two electrically charged plates. Now, charge is a conserved quantity, and the total charge remains constant. And the reason for this is that you can't transfer a fraction of an electron, you transfer the whole electron. So therefore, you cannot create or destroy charge, it remains constant. The SI unit for charge is a coulomb, and charge values in coulombs are very small. So an example, lightning bolt can be as small as 15 coulombs, so charges are very small. Charging by friction can yield a charge in the order of 10 to the negative 6 coulomb, or 1 microcoulomb, which means that if you have a charge that is 6 microcoulomb, it just means it's 6 times 10 to the negative 6 coulombs of charge. So conservation of charge, we know that electrons can't be created or destroyed. They simply just transferred from one material to another. There's no case of the creation or destruction of net electric charge, and electrons are always transferred in whole as they cannot be divided into fractions. So you have 1.6 times 10 to the negative 19th coulombs transferred for each electron. Now, a conductor is a material that allows electric charge or electrons to flow freely. And examples of conductors are usually metals. They're very good conductors because the valence electrons generally have a low ionization energy, means that they're easily removed from their atom. So the lattice structure makes it easy for the loosely bound electrons to move freely. So we can see that a lattice structure just means that all the nuclei are in a line, and it makes it easy for electrons to move. And the metals just have a sea of valence electrons around the positive nuclei rather than just orbiting. So all those electrons are free to move within between, which is what makes it easy for those electrons to be moved away from this and cause the metal to have a positive charge. And we know from the periodic table that the metals all have positive charges as they're down on the bottom left or most of the periodic table. Now the metal ions are the nuclei, that's the positively charged nuclei. We have these delocalized or valence electrons that are the ones that are easy to move to cause the metal to become ionized and have a charge. Now an insulator has electric charge, but it does not flow freely through these materials. So example, glass or rubber, kind of like paper when we had in our sticky tape activity, the paper wasn't as attractive as the foil. And unlike conductors, insulators, electrons have high ionization energy, meaning that they're not easily moved. An insulator's lattice structure is complex, which inhibits the movement of electrons, which is why the paper just had the electrons redistribute within their atom. Now, semiconductors, these are materials that can be made to act as either a conductor or an insulator. A couple of examples are germanium and silicon. Silicon is the material that are used in the solar panels that produce electricity using the sun as its source, which we'll talk about later on in this class how that works. Now, germanium and silicon are metalloids. They're along that line between metals and nonmetals and can have the properties of either, and they can conduct or be an insulator. And the reason for this is they have four valence electrons, and that gives them a higher ionization energy than metals, but a lower ionization energy than nonmetals, which means that it can act as either a metal or a nonmetal material. Now, a superconductor is a material that does not impede the flow of electrons, but this only occurs at extremely low temperatures and pressures. Now, most superconductors have a temperature of around 50 Kelvin. So you'd have to cool a material down to 50 Kelvin, or you can see the extremely low temperatures in Celsius and Fahrenheit there that would cause a conductor to become a superconductor. Now, this is not very cost effective, which is why superconductors are not readily available. Now, an ideal superconductor would operate at room temperature. Now, there's a substance called Lk99. It's a polycrystalline compound made of copper, lead, phosphorus, and oxygen. It's thought to be potentially a room temperature superconductor, but hasn't been proven yet because it has a lot of impurities in it, and that causes it to not have its superconductivity properties or prove that it has superconductivity properties. Let's look at some charging methods. So the first one we had was we did this with the sticky tape activity. Friction, when we ripped the pieces of tape apart, it transferred electrons from the top tape to the bottom tape, again using that triboelectric series. Now, second type of charging is conduction. This is where electrons are transferred without being scraped. So you have two conductors, they come in contact, and electrons are easily transferred between those conductors. So this would be like in the wintertime, you build up an excess charge because it's dry and you go to touch a doorknob and you shock yourself, which is a transfer of electrons. And the third that we're going to talk about in this video is induction. This is the transfer of electrons from one conductor without actual contact. So charging through friction, just sliding two objects together, transfers the electrons between the two materials. Conduction is a charging method through contact. So if we take two conductors and we touch one of those conductors to the other, the charge is going to transfer because it wants to be balanced. So we would just average the two values of the charges, taking into account the signs, positive or negative charges. One of them may be neutral, and they would just transfer those charge equally between the two conductors. Now, induction is more of a process in terms of charging. So we have two conducting spheres that are in contact with each other. So the first step to charging by induction is to bring a charged object close to those two conducting spheres. And you can see the distribution of the net charge. Those negative charges are going to be pushed to the sphere furthest from the negatively charged rod, which then leaves the surface closest to the rod positive. That's step one. Step two is to remove the back sphere. So you can see that the back sphere leaves that net negative charge on it. And then our third and final step then is to remove the rod completely out of the situation, which now leaves us with two charged spheres, one being positive and one being negative. Now, of course, you brought a positive charged rod, the opposite would be true. And no contact was made between the rod or the spheres with the charged object. Now, a second way we can charge by induction is if we bring a negatively charged rod to a neutral sphere, and you can see that it polarizes that sphere, pushing the negative charges to the backside and leaving the surface closest to the rod positively charged. Now we need to give those electrons an avenue to escape the sphere to polarize, so we might have a wire that's touching the ground, or have you come and touch the object and it discharges, which you get in a little electric shock. Remove the rod, and that leaves the charge on the sphere positive, and that's another charging by induction. Now, lightning uses induction to what causes the electrical discharge. So if we have a thunderstorm that moves in over a city or an open field or anywhere really, the theory is that there's ice particles that are in this clouds that are colliding, and through that they're causing them to be charged by friction. The positive collects at the top of the cloud and the negative collects at the bottom of the cloud. which if by doing this, we've now polarized the cloud. Now, because the cloud has a negative charge, that's going to polarize the ground, bringing the positive charges to the surface, meaning that the electrons are further into the ground. And then if the charge builds up strong enough, then what happens is a discharge of that cloud, much like when you shock yourself on a doorknob. And that discharge we call light, and that leaves the cloud a positive charge. Now, as that cloud moves through the air, it's going to pick up electrons from other clouds and it'll end up becoming neutral again. But this is how lightning is caused from cloud to ground lightning. And a similar process would be cloud to cloud lightning as well. So here's the summary of the charging types. Frictions are from rubbed or objects ripped apart, so the electrons are ripped from one object to another. Conduction is electron transfer through direct contact between two conducting objects, or a conducting and a insulator. In induction, the electrons are gathered or dispersed by the presence of a nearby charge, and there's no physical contact, and those have to be with two conducting or one conducting object. So now we're going to talk about the electrical forces between charged objects. So the properties, it's directed on a straight line between the two charged objects, and we saw this with the sticky tape activity. The two tapes attracted or repelled each other depending on the sign, and we can see that the spheres are going to do the same. They're going to attract each other if the charges are opposite, or repel if they're the same. It is proportional to the inverse square of the separation, so the distance between the centers. So the electrostatic force is proportional to 1 over r squared, which means that if the distance is cut in half, you'd flip 1/2 and square it, which means the force would increase 4 times. And we saw that as the tapes got closer together, their attraction and repulsion got stronger as they got closer together and weaker as we pulled them apart. The third is that the force is directly proportional to the magnitude of each individual charge, the absolute value of the individual charge. So it doesn't matter if it's positive or negative. The stronger the charge, the greater the force. And we multiply those together. And this gives us a proportion that the electrostatic force is proportional to Q1, Q2 divided by r squared. And the fourth is that same sign charges repel, so those forces would point away from each other, but opposites attract, so those forces would pull towards each other. Now, we have this proportionality, and we know from past experience that if we have a proportionality, we can change it to an equality by multiplying by a constant. So now we have an equation for the electrostatic force. Now, if we want to compare the values of Q1's force on Q2 and Q2's force on Q1, well, because those forces would be calculated exactly the same way, they would be equal in value and opposite in direction, which tells us that this is Newton's third law. So electrostatic forces between charges, Newton's third law applies, where the forces of Q1 on Q2 would be equal in value in opposite direction of Q2 on Q1. So looking at the Coulomb's law equation a little further, Fe is the electrostatic force measured in newtons. And this constant K is known as the Coulomb's law constant. And Coulomb's law constant is 9 times 10 to the 9th Newton meter squared per Coulomb squared. And this value is found by testing different charges at different distances. And it always came out that the force was calculated by using this constant. We know Q1 and Q2 are both charge values of each of the objects in coulombs. Now, if the value is given in microcoulombs or any other variable, then we'd have to calculate it in coulombs. And R is the distance between the centers of the objects, and that's measured in meters. Now, the Coulomb's law constant, 9 times 10 to the 9th, we will also might see it in terms of another factor, which is going to equal 1 divided by 4 pi epsilon naught. Now, epsilon naught is another constant, which is known as the vacuum permittivity constant. And that value is 8.85 times 10 to the negative 12th coulomb squared per Newton meter squared. So the permittivity is the ability of a substance to store electric charge in an electric field. And this is the ability of a substance, that value, in a vacuum. Now, this means that we can substitute in K as 1 over 4 pi epsilon naught. And you'll actually see both of these equations on the Physics 2 formula sheet. Now, let's look at an example. So let's say we have three equal magnitude charges, and they're placed as seen below, where Q3 and Q2 are both positive, Q1 is negative, Q1 and Q2 have a distance of R1, and Q1 and Q3 are closer together and have a distance of R2. And what we're asked to find is the direction and an expression for the magnitude of the net force on Q1. So we're going to start by drawing a free body diagram of just the electrostatic forces. And we know that Q1 is going to be attracted to Q2 because they have opposite signs. And then Q1 and Q3 will also be attracted to each other, but because they are closer in proximity, Q3's force on Q1 is going to be a much larger force. So we know that the direction is going to be to the left of that net electrostatic force. Now to write the expression, we're going to write a Newton's second law equation where the adding up the forces in the x direction is going to equal the electrostatic force calculated from Q3 on Q1. That's to the left, and that's going to be positive because it's the bigger force. And then we're going to subtract the expression of the electrostatic force of Q2 on Q1, and this would give us the expression for the net electrostatic force. Now, if you're given values, then you could go ahead and calculate it, but know that the bigger force minus the smaller force is going to give us that net electrostatic force, and it's going to point to the left because Q3's force is larger. Let's look at a second example. So now we have two conducting spheres. They're separated by a distance r. One has a positive charge of 5 microcoulombs, and the other has a charge that's negative 3 microcoulombs. And what's going to happen is we're going to bring those together, touch them, and then we're going to compare those forces when we move those charges back to the original position. So the distance is going to be the same. Now, what is going to change in this situation is when we touch them, we're going to have charging by conduction. So there's going to be redistribution of charge because those are two conducting spheres. And the way we're going to find that is by averaging the charge values. So we're going to average the values of positive 5 microcoulombs and negative 3 microcoulombs just by adding them together and dividing by 2. And what that's going to give us is a positive value of 1 microcoulomb. So that means each sphere is going to have a charge of 1 microcoulomb. Then those charges are now moved back to their original position. And now we're going to see how those forces compare to the original compared to the new situation. So before we had a 5 microcoulomb and a negative 3 microcoulomb, and after they're each 1 microcoulomb. So what we're going to do is we're going to look at Coulomb's law equation. Now, Coulomb's law constant is a constant, and the distances are the same. So we know that the electrostatic force is going to be directly proportional to the product of the charges. So that's all we have to do is look at the product of the two charges. So 5 times 3 gives us 15, and afterwards we have 1 times 1, which is 1. So before, the electrostatic force is 15 times greater than after. We also know that before we have oppositely signed charges, so that means it's going to be an attractive force, but afterwards they're both positive, so we're going to have repulsive force. So before is 15 times stronger and attractive, and after 15 times smaller and repulsive. So this is an introduction to electrostatic force, charging types, and how charges behave in materials. I hope this was helpful, and I hope you have a great day and an even better tomorrow. If you found this video helpful, click the like button down below, subscribe to my channel, Cavi Coaches, and follow me on Instagram and X @CaviCoaches.